Hello, and welcome to your neural networks lecture. So what are neural networks? Well, one thing I want you to start thinking about is the fact that neural networks are not a single type of model, like a linear regression, a decision tree, or any of the models we've learned so far. Rather, you should think of neural networks as a way of specifying the structure of your model and how you're going to train it. One benefit of neural networks is that, unlike the models that we've talked about in this class that pretty much have a fixed structure, neural networks are almost infinitely customizable. And because they have so much flexibility, they can be used for problems that simple models like the ones we cover in this class don't really touch. So what is a neural network? Well, one thing that you know is that it's a model. Just like all of the algorithms we've learned in this class, the model takes in one or more inputs and then outputs one or more outputs. But let's go over some of the vocabulary of a neural network so that you can understand what it does. The first piece of vocabulary I want to cover is a node. A node is basically just a container that holds a value. For instance, here we have a node with the value 5.27. Neural networks also have weights. Weights are really similar to coefficients. They're basically values that we multiply our inputs by in order to get some output value. Here we have a node with the value 5.27 and a weight of 0.1. The way this is arranged, it means that our value of 5.27 will get multiplied by our weight of 0.1, resulting in a new node with the value 0.527. Now, in neural networks, one node can actually have multiple input nodes that help determine its value. For instance, here we have a really simple relationship where the two nodes here, 5.27 and 2.0, are both multiplied by their respective weights and then added together in order to get the value of this right-hand node. We often also add something called a bias. You can think of this like the intercept in a linear regression. It's just a value that sort of offsets our output to be either a little higher or a little lower. The way we get the value of our right-hand node is by taking our left-hand nodes, multiplying them by our weights, and adding a bias. And typically when we show the architecture of a neural network, we don't include the biases visually, but just remember that they're there. Now, all of what I was talking about might have sounded really familiar. In fact, the thing that we built when we were defining our vocabulary sounded a lot like a linear regression. And that's because it basically was. Remember, neural networks are just a way to define the structure of models. So we can use them to define models that we already know, like a linear regression. Here's an example of what a simple linear regression predicting the amount of video game spending based on the age, the sex, the salary, and the rent of a person would look like. In this case, the nodes on the left-hand side is our inputs. These are the predictors of our model. The weights in our neural network are basically the coefficients. They're the values that we multiply our inputs by in order to get our output. Once we've multiplied all of our inputs by all of our weights, then we add a bias or an intercept, and that gives us our output value. So as you can see, neural networks can be used to define incredibly simple models. In fact, they can also be used to represent logistic regression. Here we see a similar model where we're using age, sex, salary, and rent in order to predict whether or not someone is a Twitch streamer. And the structure looks almost the exact same as a linear regression, and that's because it is. The only real difference here is in something called an activation function. An activation function is basically like a link function. It's just a transformation that we do to our outputted linear prediction in order to get a value that we would like to use. In this case, we're using an S-shaped curve in order to transform our linear predictions into a bounded 0 to 1 variable so that we can predict the probability that someone's a Twitch streamer. When we're building neural networks, we're basically telling it how many nodes we want to use and what the activation functions are that we would like to apply. So that tells you a little bit about how we can use neural networks to build models that we're already familiar with. This gives you some great examples of the things you need to think about when building a neural network. So we've talked a little bit about the things you need to think about when creating a neural network, at least in terms of the structure. We need to think about what our inputs are, what our outputs are, and how they're connected. We also need to think about any activation functions we want to use. These are just transformations of our data. But there's a second thing we need to think about when building a neural network, and that's how to train the neural network. First, we need to think about what our loss function is. Remember, we've talked over and over in this class about how a loss function is just a metric that measures the performance of our model, where smaller values indicate better performing models. For instance, in a linear regression, we often use things like the mean squared error or the sum of squared errors as our loss function. In a logistic regression or other classification model, we might use something like the log loss, aka the binary cross entropy. But we can use any loss function we want. As long as it's a number that quantifies the performance of our model where smaller values are better, we can use it as a loss function. So when you're building a neural network, you need to first think about the structure. What do you want as your inputs and what do you want as your outputs? How are those things going to be connected? Now, the beauty of a neural network is we don't just have to have those simple structures like we did with a linear or logistic regression. Instead, we can have multiple layers of nodes, thus making more complicated relationships between our inputs and our outputs. Layers that are not the input or output layer are called hidden layers, and deep learning typically refers to neural networks that have at least 2 hidden layers. So as you can see, we have a lot of flexibility with how we define our models. We need to think about the structure, so what nodes, how many layers, what the connection of those layers is going to be, and then whether or not we want activation functions for any of our nodes. Then we need to think about how we're going to train our model. What is our loss function? How do we measure how well our model is doing? Now, because neural networks have this insane amount of flexibility, they have something called universal function approximation. This is the idea that if we have a neural network that is sufficiently complex, it can model any relationship between the inputs and the outputs of our model. Thus, unlike the models we've learned so far in this class, which are pretty limited and a little bit simpler, we have the ability to model incredibly complex relationships between our inputs and outputs. This is helpful for a lot of types of tasks. Like, for instance, you see neural networks be used a lot to generate language or classify images. That's because the relationships between the inputs and the outputs in that case are incredibly complicated. So we need a model that can also model complicated relationships. Another way to think of neural networks is that they're doing feature engineering. We've talked about feature engineering as a way to just create new features, like by squaring our original predictors or by multiplying them together. Neural networks basically do this feature engineering for you. All of the layers from the input all the way to the second to last layer are basically just combining all our original input variables in various ways. You can think of this as doing feature engineering. It's taking our original variables and creating a new set of features. And we use those features to make our final prediction. Because our neural networks are typically pretty complicated, we can create some pretty useful and complex features that help us predict whatever our output is. Now, we'll talk a little bit more about the math in class, but I want to go over the ideas of something called gradient descent. Now, when we have models, even the simple models that we've been learning, we have a set of parameters that we need to estimate. For instance, the intercept and coefficient of a linear regression model. And we've had various ways of doing that. For instance, maximum likelihood estimation or least squares. However, for things like neural networks or even simpler models, it often is not feasible to directly solve for the best values of the parameters. Instead, we use an iterative optimization method in order to basically make a guess at what our parameters should be and then slowly improve that guess until we reach an acceptable value. The main way that we do this with neural networks is with something called gradient descent. A gradient is just a fancy way of saying, look at all of the derivatives of our loss function with respect to the different parameters. In other words, when we change our different parameter values, like the weights and the biases in our neural networks, how does that impact the loss? Remember, we want to choose parameter values that minimize our loss function. So when we tweak them, what does it do to our loss? Remember that when we have functions and we want to optimize them, one thing that we'll often do is set their derivatives to 0. This is because we know that when a function has a 0 derivative, it is typically a local minima or maxima of the function. Derivatives can also give you information about how to move towards those minima and maxima. For instance, let's say we started right here. At this point, the derivative is positive. This means that if we want to go uphill, we should increase our value. If we want to go downhill, we should go the opposite direction. We should decrease our value. So the derivative can tell us which direction to go if we want to go towards a minimum. On the other hand, if we were over here, then our derivative would be negative. In this case, it's saying if you would like to go towards a minimum, you should increase your value. You should go right. On the other hand, if we wanted to go towards a maximum, we should go left or decrease our value. So because these derivatives can tell us how to approach a minimum, we can use that to choose parameter values that minimize our loss function. Gradient descent can be thought of through an analogy of a hiker hiking in the hills. Imagine you're hiking in the hills and it's pitch black dark. You literally cannot see anything around you. If you needed to get to the bottom of the hills in order to get to your car or a cabin, one way that you could do that is you could get on the ground and you could feel directly around you, and you could figure out which direction you could go in order to go downhill. Then you could take one step in that direction. Then you could get down, feel the ground around you, and repeat, always taking a step in the steepest direction downhill. Well, when you do that, hopefully at the end, you'll end up at the valley, the bottom of the hills. That's the idea with gradient descent. We try to figure out what tweaks to make to our parameter values in order to go downhill, aka minimize our loss function. What ends up happening is we start at one point and we take one step in the steepest downhill direction. Then we take another step in the steepest downhill direction, and then another, and then another, and then another, and another, and another, and eventually we should end up at a local minimum of our function. Thus, we've changed our parameter values so that they minimize our loss function. Remember, lower values of a loss function mean a better performing model. So we've basically changed our parameters in a way that gives us a model that performs really well. Now, this is just a simple analogy, and we'll talk about the math in class, but this is how all of these really complicated models that you hear about are trained. Things like neural networks have a ton of parameters, and in order to estimate them, we need to use something like gradient descent in order to find the best values for all of our parameters. All right, that's all I have for you. I will see you next time.